we're going to discuss Schrödinger time independent wave equation. Generally, Schrödinger wave equation is used to understand the electronic structure of atoms and molecules, the behavior of solids and semiconductors, chemical bonding, and so on. We know that the solution of Schrödinger wave equation is nothing but a wave function which depends on position and time. If the wave function depends only on position, that equation is known as Schrödinger time independent wave equation. Whereas it depends on both position and time, then the equation is said to be Schrödinger time dependent equation. The time dependent Schrödinger wave equation is used to calculate the transition between one atomic stationary state and some other atomic state. The time independent Schrödinger wave equation is used to obtain the energy eigenvalues and the wave functions in quantum L problems, barrier penetration problems, linear harmonic oscillator, and so on. In this class, we are going to obtain Schrödinger time independent wave equation from time dependent wave equation by separation of variables. We know that Schrödinger time dependent wave equation is given by, this is the first term is kinetic energy part and the second term is potential energy part, which is equal to total energy. So as shown in equation 1.50. The wave function, the solution of this equation is nothing but our wave function. The wave function is the product of position and time coordinate as shown in equation 1.51. So wave function which depends on r, t, that can be written as separately as position and time coordinate, like psi of r and phi of t. So psi of r, t, which is nothing but the product of psi of r and phi of t. We are going to use the technique called separation of variables to obtain Schrödinger time independent wave equation. Now just to substitute equation 1.50 in Schrödinger time dependent wave equation, we will get this. So instead of psi of r, t, we are going to substitute psi of r, phi of t. So we will get this equation. Now as we know that del is nothing but partial d by dx. So del squared is nothing but in one dimension, del squared of x is nothing but partial d squared by dx squared. So del depends on x, whereas the right hand side e depends on t. So v also depends on only x. So we can take phi of t as constant out on left hand side, whereas on the right hand side we can pull psi of r, we can take it outside as constant because e depends on only on t. So pulling phi of t out as common on right hand side and pulling psi of r common outside, we will get equation 1.52. Now divide this equation by psi of r, phi of t, we will get exactly equation 1.53. So look at this equation. We have divided by psi of r, phi of t, and we have phi of t and phi of t get cancelled, and here psi of r and this psi of r will get cancelled. And we know that E equals I get cross partial d by dt. You substitute here. So instead of E, you are going to substitute I get cross partial d by dt. So this equation 1.53 becomes 1 by psi of r minus h bar square divided by 2m del square psi of r plus v psi of r, which is equal to I get cross 1 by phi of t d phi of t by dt. Now look at equation 1.54. Left hand side depends only on r, whereas right hand side depends only on t. So both can be equated to some constant e. So this equation becomes exactly which is equal to e. Now equating left and right hand side. So we can equate these two as which is equal to e, and this also can be equated to e. So left hand side and right hand side can be equated and we will get equation 1.56. So 1 by psi of r times minus h bar square divided by 2m del square psi of r plus V psi of r which is equal to E. Bring this psi of r to right hand side. We will have minus h bar square divided by 2m del square psi of r plus V psi of r which is equal to E psi of r. Look at this equation. There is no time dependent variable here. So this equation is known as Schrödinger time independent equation because it explicitly depends only on r. Now one small subdivision is there, stationary state of a system, and we know this equation very well. Now just use take right hand side term. So you have I get cross 1 by pi of t d pi of t by dt which is equal to E. You bring this I get cross to right hand side and dt to right hand side. We will get this equation 1.58. So we have d phi of t by phi of t which is equal to E divided by I get cross dt. As I said earlier, dividing by I is meaningless. You have to multiply and divide by I. You will get exactly minus EI divided by h cross dt. Now integrate on both sides. Integrating on both sides, we have this expression. So after the integration, we will have integration of d phi of t by phi of t will give you log phi of t, and integration of this one will give you t. Rising on both sides with exponential, we have phi of t which is equal to e to the power minus ei by h cross t. So we have found out one variable wave function which is connected with time coordinate, that is phi of t which is equal to e power minus ei by h cross t. We know already that separation of variable technique, we know that the total wave function is the product of the wave function which depends on position and time, the product. So substitute phi of t here, we will have this wave function which is equation 1.60. So generally for n number of electrons, the complete wave function can be written as psi n of r comma t which is equal to psi n of r e power minus I E n by h cross t. So this is for n number of electrons. So we have n here. We know that linear combination of individual functions can be written as. So this is your expansion theorem, which says that the total system can be written as sum of the individual particles. See here, right hand side we have the total system. Psi n of r comma t is the total system, which can be written as the linear combination of individual particles. So this can be written in terms of summation. So sigma over n a n psi n of r comma t. And instead of psi n of r comma t, we can substitute psi n of r phi of t. Phi of t can be replaced by e power minus I E n by h cross t. So this is equation 1.62. Now just take the complex conjugate of equation 1.62. We will have 1.63. So taking the complex conjugate, psi n of r comma t becomes psi m star of r comma t. So we have the index, we have changed n into m. Suppose if it is I, you can change it to j, which is equal to sigma over m a m star psi m star of r e power. This is we have taken the complex conjugate. So this becomes plus psi e m by h cross t. So e power minus I E n by h cross t becomes e power plus I E m by h cross t. Now you just multiply these two. When you're going to multiply these two, this equation 1.64 is obtained. Here a m star psi n of r psi m star of r e power minus I E n minus E m multiplied by t by h cross. Suppose when you're going to consider using Kronecker delta function when n equals m, this equation becomes exactly like this. So when n equals becomes, we have a n star which is equal to mod a n squared, and psi n star will become mod psi n squared, and when n equals m, this becomes 1. So anything to the power 0 is 1. So this becomes 1. We have this expression. Now look at the expression. This expression, left hand side which depends position on time, whereas right hand side it depends only on position. not on time. And this solution is known as stationary solution of Schrödinger wave equation. It implies that the electrons move around the nucleus as wave packets, which is the integral multiple of wavelength. And the formation of wave packets is similar to the formation of standing waves in sound. Now let us try to solve one problem. The wave function of a particle of mass m moving in a potential v of x is given by the wave function psi of x comma t, which is equal to a e power minus I k t minus k m by h cross x squared. Here a and k are constants. Find the expression of the potential. So we are going to find out the potential. So psi of x comma t is given as a e power minus I k t minus k m by h cross x squared. We are going to use Schrödinger wave equation and we are going to differentiate this wave function with respect to x 2 times. We are going to differentiate this wave function with respect to time only once. We are going to substitute and get the expression for potential V. That's the idea. Now differentiating equation 1 with respect to x will give us d psi by dx, which is equal to, just differentiate with respect to x. So we will have minus 2k m. This becomes minus 2x. So I have written as minus 2k m x by h cross a e power minus I k t minus k m by h cross x squared. So you just bring x inside. So we will have x e power minus I k t minus k m by h cross x squared. Now we will have to differentiate again. When you are going to differentiate again, this expression becomes. Now we have two variables here. X is here and e power minus x squared is here. So we will have to differentiate with respect to x. So keeping this as constant, we will have to differentiate this term, plus keeping this as constant, you will have to differentiate this. So when you're going to differentiate, you will get this expression. When you're going to keep this as a constant, when you're going to differentiate x, it will become 1. So this becomes e power minus I k t minus k m x squared by h cross. When you're going to keep this as constant, when you're going to differentiate, this becomes minus 2x into k m by h cross and remaining term. Now we can pull common terms out. When you're going to take common terms, this becomes minus 2k m by h cross and this is your 1. So 1 minus 2x squared k m by h cross and the common term is nothing but a e power minus I k t minus k m by h cross x squared. And we know that as shown in the problem, this is nothing but your psi. So we can write partial d squared by dx squared, which is equal to minus 2k m by h cross plus multiply this one, we will have plus minus into minus plus. So 4x squared k squared m squared by h cross psi. Now we will differentiate with respect to time. We are going to differentiate the wave function with respect to time. So wave function is given by this expression and differentiating with respect to time will give you a e power minus I k t minus k m by h cross x squared multiplied by minus k. And of course, we know that this expression is nothing but your psi. So d psi by dt is given as minus I k psi. Minus I k psi. Now we know that Schrödinger time dependent equation is given by this expression, kinetic energy plus potential energy, which is equal to total energy. Now you substitute here. So we know that del square is given by, we have already obtained for del square. So which we have inserted here on left hand side. And we are going to find out your v of psi. And right hand side already we have obtained just now, which is nothing but d psi by dt. So I get cross d psi by dt is nothing but e. So that's why I have written as I get cross. Instead of this I get cross d psi by dt, you can write minus I k psi. So there must be a psi here. Now just multiply minus h bar square by 2m inside, you will get this. Taking common terms out, here 2m and 2m get cancelled, 1 h bar and 1 h bar get cancelled, you have h bar k. And here we have this 2m, this 2 and this 4 will get cancelled, we have 2, 1m will get cancelled, h bar squared and some other will can cancel. We have remaining terms will be minus 2x squared k squared m psi plus b psi, which is equal to, we have I into I squared minus 1, already one minus is there, so plus h bar k psi. Taking common psi out, that will give you h bar k minus 2x squared k squared m plus b, which is equal to h bar k. And you this term h bar k and this h bar will cancel. You have 0 minus 2x squared k squared m plus b equals 0. So your b becomes 2x squared k squared m. So this is the expression of the potential.